Hello, I am Moonjung Park from Posttech Korea. I am presenting our work, Mitigating Oversmoothing through Reverse Process of GNNs for Heterophilic Graphs. This work has been done with my great coworkers, Jae-seung Ho and Dong-woo Kim. Oversmoothing refers to the phenomenon that stacking multiple GNN layers makes node representations to become smooth and indistinguishable as described in this image, where color of node denotes node representation. Due to the indistinguishable node representation, performance of deep multi-layer GNNs on a node classification task sharply drops, making oversmoothing a key limitation in the development of deep GNNs. Despite the shallow architecture, GNNs usually work well on homophilic graphs. This is an example of homophilic graph where color denotes node representation and shape denotes class. In homophilic graphs, since neighbor nodes often belong to the same class, learning interactions between near nodes with shallow GNNs would be sufficient. However, oversmoothing severely impacts performance, especially on heterophilic graphs in which node labels tend to differ from neighbors. In heterophilic graphs, nodes with the same labels are further apart, and thus long-term interactions have to be learned with deep multi-layer GNNs, resulting in oversmoothing. Our research goal is to improve node classification performance on heterophilic graphs by mitigating oversmoothing. Our idea is to use the reverse process of GNN layers. Let me explain our intuition with the example. These graphs display node colors which denote node representation through red and blue signal values. Chamberlain et al. Pointed out that GNN structures can be interpreted as diffusion modeled by the heat diffusion equation. As you see in the image, node representation diffuse like heat to reach equilibrium as GNN layers stacked. In equilibrium state, node representations are indistinguishable. Then, what about the node representation in the early stage of the diffusion? We can easily imagine the earlier states with peaks whose difference between those are much more clear. The corresponding graph can be expressed like this, which has distinguishable node representations. Our idea is to use reverse GNN layers to obtain such distinguishable node representations. To implement the reverse process, we designed an inverse function of a standard GNN layer. We provide three variants of inverse GNN based on three backbones model, GRAND, GCN, and JT. To implement the inverse layer, we use the numerical method for GRAND and adopt the idea of IResNet for GCN and JT. Please refer to our paper for details on implementing the inverse function. Reverse process implemented by inverse functions show nice properties for heterophilic graphs. Since node representations updated by the reverse process are more distinguishable compared to the forward process, the oversmoothing issue is mitigated. Then, it is possible to stack multiple layers to capture long-range dependencies, which is desirable for heterophilic graphs. We validate effectiveness of reverse process with extensive experiments. Firstly, we compare the node classification performance of our approaches with 19 baselines in 7 heterophilic datasets. Plus rep sign denotes models where the reverse process is applied. GCN with the reverse process achieves state-of-the-art performance in 4 out of 7 datasets and the second best performance in 1. We also evaluate whether the proposed reverse process mitigates the oversmoothing by a graph smoothness level. Value closer to 1 indicates more severe oversmoothing. In all datasets, graph smoothness level of GCN with reverse process remains low. Next, we investigated whether stacking many layers of the reverse process improved performance in heterophilic datasets. In both datasets, the performance increases as the number of reverse layers increases, which aligns with our motivation. This is the end of our presentation. Please visit our poster on July 23rd at 11:30 for more details. I look forward to meeting you online. Thank you.